of the day, where we stick with our guest planet Jupiter, and we are going to discover more about that mission that David and Jim were talking about, JUICE. And for this, we are going over live to the Kourou, which is the French Guiana Space Center. And there we hopefully have Giuseppe Sarri, who's the project manager of the JUICE planetary mission at ESA, waiting for us. Hopefully, Giuseppe, with fingers crossed, we've been having a few technical troubles with this working. Hopefully he is there. He might be on the way, he's coming. Giuseppe, are you there?
I'm mute. Okay, now I'm being unmuted. I'm there.
I can't hear you, Giuseppe, if you are there. Giuseppe, you're there. Brilliant.
Yes, can you hear me?
I can hear you. I can hear you. Thank you so much for joining us, Giuseppe. Without further ado, I'm going to hand over to you for you to do your presentation, and I will be listening intently. And after that, I'll join you for some question and answers. And when you are watching online, do put your questions to Giuseppe in the Q&A, and I'll pop them to him after his presentation. So Giuseppe, it's over to you.
Thank you very much. I will try to share this presentation. I hope we can do that. You should be able to see right now. Do you see my presentation? Hello?
Yes, Giuseppe, yes, we can see it. We can see it.
Okay, so then we can start. So good afternoon or good evening, everybody. This is from Kourou, it's early afternoon. I'm very pleased to be able to talk a little bit about JUICE. Before we go to JUICE, just a little bit introduction to set the scene. JUICE is a mission of the ESA fleet on the solar system. And you see here is a representation of our solar system with the sun on the left, where we have a couple of missions exploring the sun, solar orbiter, and so. And then if we go to the planet, we have a mission which is now on Mercury, or let's say around Mercury, Bepicolombo. We went to Venus in the past with the Venus Express, and we will go again with Envision. We went to comets, to the Halley comet with the Giotto probe, to the Churyumov-Gerasimenko comet with the Rosetta probe. Then, of course, we have a mission, scientific mission around Earth, like Cluster. We went to the moon many years ago with the Smart 1. And of course, Mars is a little bit the theme of this year, with the search of life, or remain of life, with several missions. Mars Express, ExoMars, and other missions which are in the make. Then we went to Saturn with the mission together with a colleague of NASA. It was Cassini-Huygens, and the part of the European part was to have a probe which in fact landed on the moon of Saturn Titan. Therefore, we were not yet on Jupiter, and now is our chance to go to Jupiter with the mission JUICE. And like Professor Sautud explained before, next step probably is Uranus and Neptune. So what is JUICE? JUICE stands for Jupiter Icy Moon Explorer, and that is the name itself tells that we are going to explore Jupiter, and we explore 3 of the 4 Galilean moons, Europa, Ganymede, Callisto. Why those? Because those are icy moons and they have water. I will come back to that. But before I go to the details, I would like to do a short historical excursus, because there is one scientist which was very important for the moons of Jupiter. In fact, Galileo Galilei in 1610, he found he discovered the 4 moons of Jupiter, Io, Europa, Ganymede, Callisto, that he called then now they are called Galilean moon. So this guy, he was a very good scientist. He was very good engineer, which is a characteristic that nowadays is a little bit difficult to put together because of the specialization that we all have. So he was a very good optical engineer, in fact, but not only. And he managed to prepare a telescope, or at least he improved a telescope which was already invented, if you like, by the Dutch. He polished the lenses. He had a very good telescope. He pointed to the sky, and he discovered things wherever he was pointing, because in fact that was the first telescope. And before that, people was looking with the night eye. So he pointed to the moon, he discovered to our moon, and he discovered that our moon was not a perfect system, but it has valley, it has mountain. So it was a real planet. That he pointed to the Milky Way, and he discovered that this Milky Way, and nobody really knew at the time what the Milky Way was a strip of milk or what, and he discovered that that was a conglomeration of thousands and thousands of stars. Then he pointed to Jupiter, and he discovered the moons. How did he discover the moons? The first time he looked on Jupiter was the 7th of January, 1610 at 1640. And he saw, you see in his note, and above you see a copy of his books, Sidereus Nuncius, where he described, if you like, the first observation. He saw the planet Jupiter, and he saw 2 stars on the left, to the east, and 1 star on the west. And he thought they were stars. In fact, nowadays, we can calculate back where the moon of Jupiter were, and in fact, they were exactly where he saw it. So he saw them. The only point that the 2 were too close to be resolved by his telescope, and he saw only 1. What surprised Galileo is that these 3 stars were on a line. Normally, from a probabilistic point of view, the stars are distributed on a plane. And he was surprised by this fact. And he made another observation the day after. And to his surprise, the 3 stars, they all move toward west. They were on one side of Jupiter. And in fact, there were 3 stars, 3 planets on the side of Jupiter. And that intrigued him even more, because the star should not be able to move so quickly in the sky. The day after, or 2 days after, he made another observation. He found only 2 of these stars. In fact, the 1 moon was visible, the other 2 were too close, and the 4th one was too close to Jupiter. And that, of course, another surprise for him. And then he went on pointing this telescope every night. The night after, he saw 2 stars. And then on the 13th of January, he found 4 stars. Well, he made much more observation, but eventually he concluded that those stars were moons, and those moons were having a revolution around Jupiter. Now, for us, this is so obvious that we do not notice. But at that time, this discovery was a discovery with a major impact on astronomy, philosophy, and theology. At that time, man was at the center of the universe in the overall view of people. Man was on Earth, and therefore Earth was on the center of the universe. And everything has to rotate around Earth. Nothing else can rotate if not around Earth. And he came to the conclusion, and he said, well, it is not really so always, because I found 4 moons which are in a revolution orbit around the planet. And then was let's say the footstep, the step in the foot in the door to start this revolution that came then with Kepler and Copernicus and so forth. and which generate not few problems to Galileo with respect to the current philosophy, which was the church philosophy, which was based on Aristotle. Now, so far for Galileo, which are the scientific objectives of the mission? There are two scientific objectives. The first one is to explore Jupiter and the Jovian system. Jupiter has more than 79, probably 79 or even more moon. It has a ring system with 3 very tiny rings, and it is in its own a mini solar system. And therefore, the exploration of this mini solar system by a probe which is there does allow to shed some light on the formation and evolution of a solar system. That is the first theme. The second theme, which is even more exciting, I would say, at least for a non-scientist like me, is the exploration of habitable world, which means to try to answer to the question, are we alone in the universe, yes or not? We do in many ways. For example, we point a telescope to other stars, and we try to understand if there are other worlds, the so-called exoplanet, which are orbiting around stars. But what we can do in our solar system is go to planet or to moons and try to see whether the environment there is able to support life. So how has to be a moon or a planet to support life? First, it has to have liquid water. It has to have essential elements, which are the building block for life, like carbon, nitrogen, oxygen, and so forth. It has to have a source of energy, and it has to have a stable environment. For example, Io, which is a very volcanic and unstable moon, unlikely will have life. So these 3 moons, Ganymede, Europa, and Callisto, they have these characteristics. So they are a potential, a good target for exploring existence of life. Sorry. Now, let's put this moon in perspective, because another characteristic would be to have a good gravity. In fact, these moons are very large. If you see Earth, Venus, Mars, and then Ganymede. Ganymede is almost as large as Mars. And in the bottom line, we compare the moons, Ganymede, Titan, Mercury, Callisto, and you see that Ganymede is larger than Mercury, and Callisto is as large as Mercury. So those 2 moons are basically like a planet. And the other moon of Europa, which is the interest of the JUICE mission, Europa, is as large as our moon. Therefore, the moons are large and they have gravity. And most interesting on Ganymede, as was mentioned before, it has a magnetic field. Now, the magnetic field is very important because it screens the surface of the moon from the radiation which is coming from this space. On Earth, we have life also because we have a magnetic field which is protecting us. And therefore, this heavy magnetic field of Ganymede is another bonus for possible presence or life, if you. How do we get to Jupiter? So not easy, because the gravitational pull of the sun is quite strong, and whatever we try to shoot outside of our inner planet group tends to come back to Earth. Therefore, what do? We don't have a super powerful rocket. If we would have it, we could shoot directly the probe to Jupiter, but we don't have it, even though Ariane 5, which we are launching, is quite powerful. So we do gravity assist maneuver. What does it mean? Basically, if a spacecraft passes close to a planet, close, I mean like 500 kilometers, 1,000 kilometers, so does a flyby, as we call it flyby, it also takes energy from the planet and increase its own energy. So the spacecraft can increase its speed doing a flyby of the planet. Depending where you want to go, you may have few or more flyby. So what do we do with the JUICE? So we launch in April, which is next month. After 1 year, the probe will come back to Earth in August 24 for a first Earth flyby. It will increase its energy, its speed. Then it will, in August 25, it will pass by Venus, further increase in the speed. And then it will come back in September 26 to Earth, and again, for the last time, in January 29 to Earth. Then the probe will have enough speed to escape from the gravitational pull of the Sun and to get to Jupiter. And in July 31, so 8 years after launch, the spacecraft will be in Jupiter. This phase is what we call the cruise, which is the voyage to Jupiter. When the probe will be in Jupiter, then the scientific mission will start, and we call it Jupiter Tour, because it is in fact a tour like with the cruise ship going from one moon to the other moon. And the tour will consist in passing 35 times the 3 moons, Ganymede, Europa, Callisto. Twice Europa and many other times Ganymede, Callisto, and each time there will be measurement taken, picture taken, data taken, and then downloaded to Earth in order to be analyzed. By doing that, the spacecraft will also use this flyby to change the inclination of the orbit, because so far, until the Jupiter in orbit insertion, the spacecraft is moving on the, if you like, ecliptic plane or equatorial plane of Jupiter. But since we want to explore the North and the South Pole, then the inclination of the orbit has to increase until the spacecraft is going out of the equatorial plane of Jupiter and can see the North Pole and the South Pole. Then the orbit will be put back on the equatorial plane, and the last phase will be to enter in an orbit around Ganymede. That would be the first spacecraft entering in an orbit of a moon which is not our moon. It will be a polar orbit, which means whilst the moon is rotating below the spacecraft is passing above the North Pole and the South Pole. In doing that, it will be able to see completely all the moon. End of the mission, this will be the last phase of the mission. End of the mission would be March 35, so quite far from here, from now, and it will end with the crashing the spacecraft on Ganymede. We were talking about, I'm talking about the spacecraft, but in fact, to make a mission, you need more than just a spacecraft. You need a launcher, because you have to put the spacecraft in orbit, and this is called Ariane 5, the European launcher. When the spacecraft is in orbit, it needs to communicate with the Earth, and in particular being very far, because Jupiter is far, 700 million kilometers. We need big ground station, big antenna, and we have 3: Cebreros, which is in Spain, New Norcia in Australia, and Malar in Argentina. So these ground stations are, one is on the upper northern hemisphere, the other 2 are in the southern hemisphere, which will allow to always see the spacecraft, regardless if it is above or below our horizon. Then all the data have to be downloaded to somewhere where the spacecraft is controlled, and there is a Mission Operation Center in Germany. It's called ESOC, stands for European Space Operation Center. It's from where we operate all our spacecraft. And of course, there is all the scientific part, which is the reason why we are building the spacecraft. which is located in Spain. And there is a big community of institute scientists who has provided the 10 instrument of JUICE. That's the spacecraft. Spacecraft is now here in Kourou. So it's a big spacecraft. It does make 6 tons, and most of it is propellant, 3.6 tons of propellant. And the reason why we have so much propellant is because our cruise is very long. We need to do a lot of correction maneuver. And when we enter in the orbit of Jupiter, we have to brake because we are coming so fast that we will not be able to be captured by the planet if we do not decelerate. So we have a big main engine, which is mainly used to decelerate, to slow down the spacecraft. You see big solar array, 85 square meters of solar array. In fact, the difficulty in Jupiter is that it's being very far, it is very cold, and there is not much sun. And therefore, we have 85 square meters of solar array, but we collect only 800 watts. The same solar array, if we will put on a spacecraft around Earth, will collect 24 kilowatt, 25 times more. In Jupiter, only 800 watts. So the spacecraft has to be very, it has been designed not to consume too much power. One other thing which you see, where you see the small man, is a big antenna, again, big because spacecraft is far. And if we need to communicate to Earth and to send a lot of information, we need a big antenna. Mostly, all the instrument will be on the upper face, which we call the nadir face, is the face which we look to the moon when we do the scientific mission. We have 10 instruments. I will not go through all of them, but it is important to describe a little bit in order to understand how with instrument we can explore a planet. So the first group of instruments in the blue part that we call remote sensing mainly means instruments which are looking at in a wide wavelength range. So not only the visible. So we have an optical camera that we make a real picture. We have infrared spectrometer, which will look into the infrared. We have ultraviolet spectrometer in the UV ray. And we have a sub-millimeter instrument, which is looking on the sub-millimeter, on the wavelength of our microwave, for example. And the fact that we can look to something, not only on the visible, but on an enlarged wavelength, on enlarged frequency, allow us to know more about what we are looking at. But that will give us the understanding of the surface. Then we need to understand the inside. To understand the inside, we have 3 instruments. One is a laser. Basically, we send a laser pulse. The laser is reflected by the moon back to the spacecraft, and we measure the time for this pulse to go and come back. And from that, we can we can understand the profile of the moons. So we can see whether there are valleys, whether there are mountain and crater and so forth. We can really map, we can do an altimetric map of the moon. Then we have a radar because we want to look inside. Now with a radar, with the proper frequency, we can in fact, the signal go below the surface of the moon, it crosses the ice layer and it go into the ocean until it get the bottom of the ocean, and then it's coming back. And by measuring how this coming back wave has been deformed, we can understand where there was a transition, like where there was a transition from ice to water, and how deep is, for example, the ocean. And last but not least, we have an instrument that will measure the gravitational field. Because if the moon would be a pure, perfect ball of stainless steel, the gravitational field around would be perfect. But if there is, in fact, a distribution of the mass inside, like there is an iron core, and maybe there is water, there is ice, these change the gravitational field around the moon. So by measuring this variation of the gravitational field, we can understand how the mass is distributed. So putting together the laser, which look into the profile, the antenna which is going inside, and the measurement of the gravitational field, we can map the inside of the moon. And then in green, last but not least, there are instruments which are measuring the characteristic of the space, all space that we will find from Earth up to Jupiter. So we will measure magnetic field, electrical field, how many particles there are, heavy ion, proton, electron, neutron, and so forth. So those are the 10 instruments. Now, a few pictures. In this picture, you see a big chamber. In this big chamber, there is our spacecraft without the solar array. And this chamber is then closed, and we make vacuum. Well, we have made vacuum because the test we did 2 years ago. And we can switch on a simulation of the sun. In fact, we can switch on light, a light beam, which has the same characteristic of our sun. And doing this test, we can verify that the spacecraft will be able, when in space, to survive the environment in the range of temperature, which is extremely high, very hot to very cold, and will also be able to survive of the temperature and the vacuum that we have in space. This is the first important verification that we need to do, and all spacecraft will do. This is a picture, a view of the spacecraft from the side of the Huygens antenna. You can see how big it is compared to the man. And on the left, in black, you have a small antenna, because in fact the white antenna is fixed on the spacecraft. And when we measure, when we look to the moons, this antenna is looking somewhere else. It's not looking to Earth. But we always want to be in contact with our ground station, and therefore we have this black antenna, which is which we can steer in 2 dimensions, and we can always keep pointed to Earth. Then we need to do also a set of mechanical tests before we say that we can launch the spacecraft. On the left is the clamp band release. What does it mean? The spacecraft is mounted on the rocket, on the top of the rocket, but is not, the interface is not bolted, because otherwise we will not be able to separate the spacecraft from the rocket. There is a belt, which is called clamp band, but it's kind of rim belt, which keep 2 flanges, one on the spacecraft side and one on the launcher side together. After launch, this belt is released, is open, and there are springs which are pushing the spacecraft away from the launcher. However, this action generate a shock, which can damage the instrument on the spacecraft. Therefore, we need to do a test. Then on the right, the spacecraft is on a shaker, so is a plate, is a table, which is placed in vibration, vertical vibration, horizontal vibration, to the same vibration level that the spacecraft will experience during the launch. But it's not finished. During the launch, there is a lot of noise coming from the engine, and the noise, I'm talking about under 20, under 30 decibel, is an unbearable amount of noise. And this noise is generates a vibration, and this vibration can damage the spacecraft. So this is the last test that we do. So the second group of tests, which I just described, are those which will allow to confirm that the spacecraft will survive also the launch. So the spacecraft is to survive the launcher and to live in space. And with these two kinds of tests, we can prove that. This is a picture in which you can see a solar array. We have very large solar array. The solar array are in a cross configuration. In this picture, you only see the linear part. So because it is impossible to do the deployment of the solar array in one single shot. So this is the beginning of the deployment, but this picture gives you a feeling of how big is the spacecraft and the solar array is compared with people. So let's come now to the present. We arrived here in Kourou, Cayenne Airport on the 9th of February, almost 1 month ago. The spacecraft was in this gray transport container, and the transport container was transported with with the biggest aircraft that exists, which is the Antonov Under-24, from, as you can see from the flag, from Ukraine. We had some doubt. Unfortunately, the start of the war has also some impact that, for example, a set of transport aircraft were not available, those provided by the Russian, but the Ukrainian one were still available and they are commercialized by Ukrainian airline. And then this is the spacecraft here. You don't see the solar array. In fact, on the top and on the bottom of the spacecraft, you see this kind of sandwich. Those are the solar array folded, and they will stay folded until launch. So coming toward the end, in summary, we launched with Ariane 5, the European launcher. V8 260 means Vol Ariane 260, means is the flight number 260. So before us, there were 259 flights of Ariane, and after us, there will be only one. So we are the one before the last Ariane 5 flight. Launch date is 13th of April, 12:15 UTC, Universal Time Coordinate, which make 9 o'clock here in Kourou and make 2 o'clock in the afternoon in Paris and 1 o'clock in the afternoon in London, I believe. And the launch window, we have a launch window. We cannot launch any time of the year. And our launch, we can only launch up to the 30th of April, and then we have to wait. And the reason is because, if you remember, before I was talking about gravity assist maneuver. So we launch, the spacecraft has to meet the Earth, take the energy, go to Venus. In order to do that, all these planets has to be in the right place at the right moment. And that is happening for this mission only twice per year for 20 days, in April and in August. So if we miss a launch date now, we have to go in August. And if we miss August, we have to go to the next year. Each mission of ESA has a logo, and the project can decide how to make a logo. And the logo is basically, you will see then in the animation that I have, on top of the rocket, there is a space of 3 meters by 2 meters in which we can put whatever we want. Of course, it has to make a relation with the mission. And what we did 2 years ago, we made a children competition among children on the world, asking them to make a drawing representing our mission. And the winner was this nice drawing in which you can see Jupiter very happy to get juice, and the 3 moons a little bit shy because they are shy of being explored by some external guy, but we will. This logo was drawn by a Ukrainian girl, 9-year-old, name is Yarina. There is no political consideration here because, in fact, the selection was done before the war was starting. But is a funny coincidence, I would say, or maybe not funny, is a coincidence. Now, before I conclude, I have two animation, and I hope I can run the animation in team. And the animation, the first one is showing the launch. So basically, this is the launcher. This is in fact Kourou. There is a launch base which is basically in the middle of the jungle. This is the rocket with the logo. Inside the fairing, there is the spacecraft. 7 seconds before liftoff, the main engine will be switched on, and then after basically switch on in order to check that everything is fine, and then the spacecraft, the launcher will lift. It will be pushed by the main engine and by the two lateral boosters. The two lateral boosters are so-called powder booster, while the central one is burning liquid hydrogen with the liquid oxygen. The two lateral boosters will burn for 2 minutes, and then they will be switched off, and they will come back to Earth, or better, they will come back on the Atlantic Ocean. You see the powder which is burning, and now they will separate 2 minutes after launch. Now the rocket is propelled by the main engine, and 3 minutes after launch we will open the fairing. Not before, because otherwise the friction with the air will destroy the spacecraft. The main engine will burn for another minute, so 3 minutes after launch, there will be the separation of the main stage. Up like that. And we will switch on the upper stage. It's a 3-stage rocket, like almost all rockets. This upper stage will work for other 20 minutes. You see that there is a rotation. This we do in order to make the temperature on the spacecraft uniform, because we are in the sun. We don't want to have always the same side of the spacecraft on the sun. It's called barbecue mode. And then 28 minutes after launch, the spacecraft will be released in a configuration with solar array closed. Now, the first 30 minutes, now what do we do with the spacecraft? The first 30 minutes will be done in automatic way. So no ground control. The first things is deploy one solar array. That deployment will take place 50 minutes after launch. Then we will deploy the second solar array. And then at this point in time, the control of the spacecraft will be taken by ground. And by ground, all the other system will be deployed, like the small antenna. This is what is deployed now, is the long antenna which we will use to see in the depth of the ocean of the moons. So it takes some time to deploy it because it's folded in several bits and pieces. And after that, we will deploy several booms, which on the tip of them, there are instruments. So this is a 10-meter long boom. And on the tip of this boom, there is another antenna. And then there are few other booms which will be deployed, in fact, and that will complete the configuration of the spacecraft. At this point in time, the work is not done because we need to switch on many other units inside the spacecraft to check that everything works perfectly before we can hand over the spacecraft to the scientific community. And That concludes my presentation. I hope.
Thank you so much.
You are still there.
I am certainly still here. I've been listening intently, as I'm sure lots of people have been online as well. And I've got time for just one question for you. And my question for you is, you're the project manager of this. Now, this is such a huge, excuse my words, but mission to meticulously plan when it's going to do the flybys and how things have to sort of all slot together to make it happen. How on earth do you go about planning something like this? And I suppose you've got to meet all the teams, like you slipped in that you didn't have a scientific background, so you have to meet them all, understand what they're doing, meet their needs, and come up with this amazingly precise schedule. That can't be easy.
Yeah, I think one of the biggest efforts that we have to do is an effort of coordination. We have to coordinate the spacecraft, the building of the spacecraft, the building of the launcher, which has to come at the same time with the spacecraft, the development of the ground segment. We are talking about, in the peak of our activity, about 3,000, 4,000 people working all together. So it's really, of course, there are procedures, there are processes. We are not inventing the things from scratch. We know how to do it, but is a big work of coordination, talking with people, in particular for the scientific mission, because the scientific mission is there to let all people of Europe work together, all industry of Europe, all scientists of Europe. It's not like only one country does it. It could be much easier, but that is the purpose of science, to put the people all together. And this is what makes the coordination work a little bit more complex.
And that has been a bit of a theme of today, of like working together. And it's a way that I suppose that Mars is bringing the nations together, because to go on such a large mission, no country can really do it alone. So we have to all work together, and especially for going to, these new moons of Jupiter. Gosh, like those new missions there. Yeah, it's about that collaboration, isn't it?
Yeah, it's collaboration, which is, as I said, the drawback that is much more difficult. It's much more funny. I think it's much more nice to do that. And it also allowed to put the right amount of money to do mission, because this kind of mission are very expensive, and no single state of Europe will invest the money to do that.
Yes, there's multiple reasons why it works. Well, Giuseppe, I will certainly have my fingers and toes crossed for the launch, and I hope it all goes smoothly. I will be watching. But thank you so much for filling us in on those missions and hosting the describing the mission to our guest planet here on Mars Day. So thank you very much.
Thank you very much, and it was a pleasure to do that. Bye.
Brilliant. Bye-bye. And that was our last session of Mars Day 2023. Now, what I would love to do is give a big thank you to all of the crew that we have had working away all day and all yesterday, getting everything set up. It's no mean feat getting all of these feeds in, especially from French Guiana, but we did it. So well done to everyone here. Well done. And of course, a big thank you to you who have been watching online. It would be nothing without you viewers, so thank you so much for watching and expanding your knowledge when it comes to Mars, and of course the guest planet that we've had, Jupiter. Now, this is going to be the end of Mars Day, but as we've been saying all day, it is Mars Week, and there are lots of events coming up. We have some online lectures, there is stargazing, both online and in person, and there are these debates that are going on, some online, some in person. And so do have a look on the Mars Week website and check out those events, because there's so many ways you can get involved. And I've got a little bit of knowledge for you. The Mars Day for next year, I can announce that it will be on Tuesday, the 5th of March, 2024. So get that date in your diary right now, and hopefully we will see you next year. But for now, that is it for Mission Control, and happy Mars Day 2023. Thank you.